We find carbon in the food we eat, the clothes we wear, and the fuels that power our cities. It is a material that functions as a structural architect across both the physical and biological worlds. This versatility begins with its atomic structure. Carbon possesses 6 protons and an outer valence shell containing exactly 4 electrons. For an atom to achieve stability, it typically needs to fill its outer shell with 8 electrons. However, carbon's nucleus only contains 6 protons, which lacks the energy required to capture and hold 4 additional electrons from other atoms. At the same time, giving away its own 4 electrons would require a massive energy surge, not found under normal conditions. Because carbon cannot easily steal or surrender electrons to form ionic bonds, it is forced to share them. This physical constraint is what allows carbon to act as a universal connector. This process of sharing creates covalent bonds. By linking with other atoms, carbon can satisfy its need for 4 stable connections. In a molecule of methane, or CH4, every one of these 4 bonds is identical in energy and length. But carbon's ground state electrons actually exist in different types of orbitals, the s and p orbitals, which possess unequal energy levels. In 1931, chemist Linus Pauling proposed a mechanism that reconciled this energy difference with the physical reality of the molecule. This is hybridization. When carbon prepares to form bonds, it takes its unequal s and p orbitals and allows them to intermix and reshuffle. The result is 4 brand new, energetically identical pathways called sp3 hybrid orbitals. To minimize repulsion, they lock into a 3D tetrahedral shape, separated by an exact angle of 109 degrees and 28 minutes. This internal reorganization is the precise mechanism that allows carbon to form stable single, double, and triple bonds, connecting with itself and other elements in a variety of configurations. When carbon bonds only with itself, it creates allotropes, materials made of the same element that exhibit vastly different physical properties due to their internal geometry. In a diamond, each carbon atom uses sp3 hybridization to link with 4 others in a continuous 3-dimensional network. Because these bonds are incredibly strong and the tetrahedral structure is so rigid, diamond is one of the hardest materials known. Shifting the geometry to sp2 hybridization creates graphene. Here, the atoms form a 2-dimensional hexagonal sheet that is stronger than steel, yet entirely flat and electrically conductive. These same hexagonal sheets can also curve. In a Buckminster fullerene molecule, 12 pentagonal and 20 hexagonal faces come together to form a hollow, soccer ball-shaped sphere. When those hexagonal sheets are rolled into cylinders, they become carbon nanotubes. These structures are under study for use as molecular wires in integrated circuits, replacing traditional copper. By altering the geometry of its bonds, pure carbon can transform from a hard crystal into a 2D sheet, or a cylindrical conductor, providing a shape-shifting foundation for advanced materials. For years, it was believed that the complex carbon compounds found in living things could only be produced by a biological, vital force. That theory was disproven when Friedrich Wöhler synthesized urea, an organic compound, from inorganic starting materials in a laboratory. This laboratory synthesis highlighted the role of functional groups. These are specific clusters of atoms, like hydroxyl or carboxyl groups, that attach to a carbon skeleton. When they snap onto the chain, they dictate the chemical behavior of the entire molecule. Organic chemistry operates like a modular engineering system. The carbon chain serves as the universal chassis, while the functional groups act as interchangeable accessories that determine what the molecule actually does. This modular system is powered by catenation, carbon's rare ability to link with its own atoms to form stable, incredibly long chains. Some proteins found in nature contain millions of carbon atoms linked in a single molecule. Carbon also exhibits isomerism, where 2 compounds use the exact same ingredients but arrange them into different architectures. This allows the same 4 carbon atoms to form a straight chain, like N-butane, or a branch structure, like isobutane. The combination of infinite catenation and structural isomerism allows carbon to generate millions of unique compounds using a very small set of starting rules. Carbon functions as a highly adaptable system for building complex, stable structures. It is the primary operating system for life as we know it. The atomic rules of electron sharing that define a simple methane molecule also govern the construction of carbohydrates, proteins, and human DNA. The vast complexity we see in nature is built upon carbon's unparalleled ability to share energy and adapt its own structure.